get started looking at doing t-tests. So here we're going to be looking at doing an assessment of the means of two different samples and comparing them to each other. We're going to get started working with independent samples, and then next week we move on to dependent samples. So here really quickly looking at it, it's actually a little bit easier to define a dependent, or often called a matched pairs sample, and use that as your base point, and then if it's not meeting those requirements, we would consider it independent. So when we're looking at a dependent or matched pairs sample, these are two sample values that are somehow matched together in a meaningful way. So we have some examples over here on the right that are really common, doing a before and after assessment for an individual, for an intervention, matching up two individuals on a meaningful characteristic such as a parent-child. You might see, for example, a lot of this in education where you're looking at parents' education level or parents' income and comparing it to their child's performance in school. And also sometimes to control for certain variables. So, for example, if we're looking at women who survive breast cancer and women who without breast cancer, and looking for some important differences between them, obviously this is something that we can't control, but we can in fact match these women up with similar characteristics. So in a situation like that, I might recruit women with breast cancer and then collect information on them, on their religions, their family structure, their socioeconomic status, level of education, other factors like that. And I would then match them with another woman that meets them on all of those similar characteristics but does not have breast cancer. So that's another way that we can do a type of dependent match pairs. If we're working with data that we don't have any reason to believe is connected together, we would start with the assumption that it's not. So we would assume they're not connected in any way unless there was good plausible reason and evidence to connect them together. If there is not, we're doing independent samples t-test, and as you can imagine, this is one of the more common ones we use. So your book goes over several different forms of the t-test. We are going to focus on doing the t-test when our sigma for both of our populations is not known, and we are assuming that it is not equal. So we have sigma, the standard deviation for the population 1, standard deviation for population 2 is unknown. We are assuming that they are not equal to each other. This is the most common one that you're going to use, so we're going to focus on that. Do be aware that there are other approaches that would use if you did know the standard deviation for the populations, or you had some reason to believe that they would be equal, but we're not going to go into those right now. So we're going to work with some practice problems here. Practice problem number 10 on page 458, and let's kind of go through this together to get us oriented to the steps we're taking for solving this kind of problem. So here we have our sample summary data. We're given a significance level of 0.01, and we're being told to test the claim that men and women have different mean body temperatures. So the first thing we need to do, looking here at our steps, is we need to go through and check our requirements. Our requirements here for an independent samples t-test, it has to be a simple random sample, has to be independent, as we just discussed. Here we're looking at our values for the standard deviation for both of our populations are not known, and they are not assumed to be equal. And lastly, we need to have either both of the samples need to have an n greater than 30, or both samples come from populations with normal distributions. So looking at our example over here, we can see that we do not meet that first criteria. One of our n for group 1 is only 15. However, we're told in the problem that we should assume that they are normally distributed factors within the population. So we, in fact, meet these criteria. All right, now the next thing we need to do is we need to identify the claims that we're testing. And remember, we need to set this up in terms of the particular population parameter we're working with. So here we're looking at mean body temperatures, so we're working with mu. So all of our statements from here on out are going to be related to mu. Now, I find it easier sometimes to set the alternative hypothesis first. So sometimes I skip to step 3, because when we're looking at the claim that they're giving men and women have different mean body temperatures, that's actually what they're telling you is going to be the alternative claim. So that tends to be what they give in the language. And so I use that first to set step 3. As you can see here, and then after you have that, remember go back up to step 2. Remember that our null is always going to be set as equal to. So hopefully we've got that clear in terms of setting up step 3 and 2. And like I said, I sometimes find it easier to actually do step 3 first and then come up to step 2. If that works for you, that's fine. Now, our last part here for step 4 in this setup is writing in terms of hypothesis formula. And so we would have, again, our HO, our null, is mu1 is equal to mu2. And our alternative, H1, is mu1 is not equal to mu2. Because again, we've been told simply that they're different. We haven't been told that they're less than or greater than, but simply different. Okay, so now we're going to identify the specified alpha. So looking at this problem, can you identify the specified alpha that we're going to use for this particular problem? It's going to be our 0.01. So remember, when you're putting your directions and developing your notes, pay attention to your language. Alpha is the same thing as significance level. So if I have a significance level of 0.01, my alpha is also 0.01. So alpha and significance level are two different terms used for this, replying to the same number. So make sure you've got that clearly in your notes so you're not causing yourself unnecessary confusion there. Now the next thing I need to do is I need to identify my relevant test statistic. So we're going to go again to that table that we've been using, and we can see here I'm talking about a mean. So I'm in the middle of this table, and the next question we need to ask ourselves, we can see either we're going to use a t-distribution or the z-distribution. That's going to hinge on whether or not our the standard deviation for the population is known or not known. So in our situation, our standard deviation for our populations are not known. Okay, so when we're looking at this, we can see that we're going to be solving for a t value. So that identifies our test statistic, and that's what we're going to be solving for from here on out. Okay, now we're going to calculate our test statistic. Now here is the formula that we use for calculating our test statistic if we've been given this summary pieces of data here. So we use this when we assume that mu1 minus mu2 will be equal to 0. We'll look at a moment where that language comes from, kind of hold that in the back of your mind, and we're going to come back to why we're working with that assumption in just a moment. But for the problems in this class, we will be working with the assumption that mu1 minus mu2 is equal to 0. So if we look at this, we can see where we're going to take each of our numbers and plug them in. So pause here for a moment and write this into your notes. Go ahead and take this t formula, writing on both the plain formula, and then go through and plug in your numbers from your summary chart, keeping in mind that when you're plugging in your x1 minus your x2, that's going to be followed by minus 0, because we're assuming that mu1 minus mu2 is equal to 0. So pause the video here so you're sure that you can take these different numbers from the summary chart and plug them in to that equation. And when you finish with that, turn the video back on and let's go to the next slide together. Okay, so here we have the formula with my numbers plugged in. If you pause the video for a few moments here again, go through and do your calculations and see what you get for your t. Turn the video back on to check. I should get a t obtained of 1.559. However, remember our rounding rule. When we're working with summary information, we round to the same decimal place as the summary stats. So our actual t obtained is going to be 1.56. Now notice I've actually put t OBT. That's another symbol sometimes I like to use instead of the test statistic. So you can be using any symbols you want, but again, be sure, I find it helpful to clarify between the t that I'm working with that I've obtained through my calculations and the t critical value that I'm looking up for. If I don't distinguish between those two, it becomes very easy for me to become confused as to which one is which. So here we have our t obtained is 1.56. Now we need to determine our critical value, our t critical value. So what is the information I need to look this up? When I'm locating a critical value with a t distribution table, what are the three pieces of information that I'm going to need to have? I'm going to need to have my degrees of freedom, my alpha, and I'm going to need to know if it's a left tail, a right tail, or a two tail. So let's go through and look at identifying each of these pieces. So degrees of freedom, I'm going to take the smaller of the two options. So I'm going to have the n of 1 minus 1 and the n of 2 minus 1. So we're going to use the smaller version because we're using the more conservative option. Remember, whenever in doubt, in statistics, choose the more conservative option. So here I'm going to be using my N1 population, where I have 15 minus 1, so that gives me a degrees of freedom of 14. Right? We already have my alpha's already been given to me as 0.01. And the last question here is whether I have a left tail, right tail, or a two-tail test. Now, pay attention here to the language in the problem. If it's asking me to solve for a difference, then I'm conducting a two-tail test. If it's asking me to solve for a value that's greater than, I am conducting a right tail test. If it is asking me to solve for the value that is less than, I am solving for a left tail test. And then for those individuals that are finding this difficult to assess which particular type of tail test you're solving, I suggest you put this explicitly right here, same thing as I have it here, into your notes to help you make sure that you're able to correctly identify which type of tail test you have. So using this language here, what type of tail test do we have that we're solving? A left, a right, or a two-tail? We will be solving for a two-tail test. Now we're going to take this information and we're going to go look this up in the T distribution table to find my T critical value. So take this information and you go in your T distribution table and you're going to look this up. So you're going to look for degrees of freedom of 14. You're going to work in the chart for the table that's a two-tail test, and you're going to look for the value of 0.01. So if you're locating that, what is the T critical value that you find for this problem? You should have found 2.977. Now, this is going to be plus and minus because it's a two-tail. So here we have to have both a minus 2.997 and a plus 2.997 to proceed. So make sure you're clear about that as well when you're solving a two-tail test. It has to be a positive and a minus. You have to have two values. Okay, so now we've got my T critical value. What is going to be my next step? What do I need to do now? I've got my T obtained, my T critical value. What do I need to do? Well, I'm going to need to graph them out and assess the location of the test statistic, right? So here's my next step. So I'm going to go through and do the graphing. And here's this graph written over here to the side. It's just something that looks like this. So I've got my T critical value to the left and the T critical value to the right for both my negative and my positive. Now, question here. Which area of this figure is going to be the rejection region for this problem? Is it going to be the option in between my two critical values, or is it going to be the option outside to the left and right of my two critical values? So make sure you're clear about that when you're labeling your figure. It will in fact be the outside regions here are rejecting the null hypothesis, and if it falls within those two ranges, we're going to fail to reject the null hypothesis. So now that I have that, my next step is plotting my T obtained, my 1.56. So take a moment and look at where is that going to go in this figure. It's going to go here. So here's roughly my T obtained 1.56. So now I've got to assess my rejection. So do I reject the null if the test statistic is within the rejection region and I fail to reject it if it is not within the rejection region? So looking at this situation with our data plotted now, am I going to reject the null or fail to reject the null? I'm going to fail to reject the null. So now that I've failed to reject the null, I need to restate this decision in non-technical terms to address the original claim that we have specified here. We're going to go back and look at the language for awarding our final conclusion that we have in the flow chart. Keep in mind, again, that's posted on Blackboard under additional materials. And our statement is going to be there is not sufficient evidence to warrant the rejection of the claim that men and women have the same body temperature. In other words, there is not sufficient evidence with these samples to indicate that men and women have different mean body temperatures. This concludes our option of going through and looking at this, doing the critical value method for solving an independent samples t-test. The next video will be looking at solving for p-value and using StatsCrunch.